when we were looking at the confidence intervals for the true mean previously, we were making an assumption that somehow we knew what the population standard deviation was, and we were developing based upon our sample set what the confidence interval was for the true mean. But most of the time we don't know what the true population variance is. We might have some prior information that suggests what it might be, and we can go along with that, but oftentimes we don't. However, we do have that data set, right? So we could use that to estimate sigma x with our sample standard deviation, where we defined that sample standard deviation to be equal to the square root of the sum of the xi minus the sample mean squared, all divided by this n minus 1. That n minus 1 was key, remember, because that gave us an unbiased estimate of our population standard deviation. Or rather, really, that gives us the unbiased estimate of our sample variance, and then we take the square root of it, and there's our sample standard deviation. Okay, so what we're going to end up doing then is we're going to replace u with a new statistic, and that statistic will be a capital T with a subscript of n minus 1, and that's going to be equal to the sample mean minus the mean of x, population mean now, divided by the sample standard deviation divided by the square root of n. And now one of the keys here is that this new sample statistic is, when we do this replacement, is not necessarily Gaussian, or that's another fancy way to say it's not necessarily a normally distributed random variable, because now in the construction of it, instead of having one random variable that was approximately normal, we now have another random variable, sample standard deviation. Right, so that makes then this new statistic not necessarily. Indeed, though, what it does have, if our underlying distribution for x is normal, then t has a student's t distribution. Student came up with this distribution, and so it's the t distribution, and it has n minus 1 degrees of freedom. Okay, and as n gets larger, then if it gets large enough, the t distribution will turn out to be normal with mean of 0 and standard deviation of 1. Let's take a look at what this distribution looks like in terms of shape with a figure in your textbook. We have in figure 8.4 a variety of different t distributions plotted. Here's one with k equals 1 degree of freedom, right? Lower height, it's still a bell shape. It's very much like the normal distribution, but it's going to have fatter tails, right? Lower height here means we have to push area out into the tails. So that's k equal 1. And then for a larger number of degrees of freedom, then we get higher in the middle, lower out in the tails, and then as k goes to infinity, we get that standard normal distribution all the way up at the top. And so there is that kind of question of, well, how close do we have to get to, how large does k have to be before we get to something pretty close to the normal? And so certainly k greater than 30 in some views is going to be close enough. Some people will say 40. Other people will actually even lower this and say, from a practical reason, we might be possibly as low as 20. A little bit depends upon what the underlying distribution is of things at stake, how fast we converge to the normal distribution in its underlying process. So the 30 number is not a bad one to be looking at. Now, in terms of building those confidence intervals, and we'll still focus on the two-sided one, if you turn to figure 8.5 in your text, it's going to be the same kind of thing here, where we have areas sitting out in the tails. The thing that you have to be careful of is, what does alpha represent? And I don't even like to try to keep track of all that. I think about this more physically. And that is, if someone tells me you want to go construct the 95% two-sided confidence intervals, I say, aha, two-sided. That means central body of the area this is 95%. And so 1 minus that is going to be, okay, 5%. And then I'm going to divide that up into two equal areas, typically. So I just try to think about it physically rather than keep track of all the symbols. Does alpha mean exactly the same thing? Before this was alpha over 2. We're going to run into cases here in a moment where no, alpha is really only out in the one tail, and that just gets a little kind of confusing, I think, in terms of the notation. But this is what your author is using here. And again, I say, if you just think through it physically about what you're trying to accomplish, that's the key element, and that will guide you correctly every time. And if you try, though, to do a formulaic approach to this, it can get quite nasty real fast and easy to make a simple mistake. And usually that mistake is, did you double the area out there, or did you only use half the area that you're supposed to use out there? So let's illustrate this with an example. We're going to revisit our fatigue data, where we had x bar was 26.75, n was equal to 16, and now our sample standard deviation is equal to 20. When we were constructing the confidence intervals the first time, we were assuming that the true population was equal to 20, and so having this small little subtle change will illustrate the difference between having substituted in with the sample having a small set in the small size of the sample also. Okay, and so our n minus 1 is going to be equal to 15, so that's our number of degrees of freedom. And so we're looking at this interval for t here with 15 degrees of freedom between a lower bound and upper bound of T1 and T2. And so when we go to look up these values here, this cumulative for T2 is going to be 0.975, right? We're doing this two-sided 95% approach. Okay. So back here in Appendix A, page 711 of your textbook, or Table 5, they call it percentage points of T alpha comma nu of the T distribution. Right? So the alpha, what you have to really pay attention to is their figure that tells you what alpha is supposed to be. And alpha is noted as the percent that's sitting out here in the tail. Right? And this new thing is the degrees of freedom. Now, a lot of other tables will actually write that directly, and you might want to do that for your own use. Just write degrees of freedom right in that location. Okay, so our degrees of freedom are in the column at the far left. They actually represent rows. So there's our 15, and then here's our tail percentage. We wanted 95% two-sided. That meant 2.5% out in the tails. And here again, you have to be careful because sometimes they'll write this as a decimal, sometimes they'll write it as percent. So you just have to keep track of what it means, and usually by context you can kind of figure out what they're doing in this particular case. Right? Now if they don't include the little table and a figure like this one does above, then you get real concerned, and you have to sort of practice a couple and know a couple of numbers right off the top of your head just to kind of figure out, reverse engineer what they've done. This one is fairly direct. You can reverse engineer what's happening here. 15 degrees of freedom, 0.025 out in the tail. That t-value is 2.131. So from our table, two-sided, 95%, then our t-value is going to be equal to plus or minus 2.13. Okay, and so our interval will be x bar plus or minus 2.13 times our sample standard deviation divided by the square root of n, not n minus 1, but of n. Right, and that will give us an interval of 16.1 to 37.4. And note that that's going to be wider, right? And that will always be the case for practical situations. That with unknown variance, these confidence intervals using the t-distribution will always be larger for these large confidence interval levels. Right, I suppose there might be some pathological case where something gets pulled in. Or is it? That's an interesting question. Let's go back and look at whether you could ever get some sort of pathological answer here. And if we come back to our t-value, note that we have an interesting crossover point that seems to be happening at the same location. Right, so that's an interesting question of if you were to go and solve for that point, what area would it be that the normal distribution and the t-distributions all had the same value down here for their standard variant value? Is that a common point, or does it just look like that plotting wise? I'm going to leave that up to you. It's a sort of a thought exercise to go figure out, see if you could ever end up with a case where you're a small, like a 50% or a 20% confidence interval. Do you actually get a smaller t-distributed one? There's not a lot of practical significance to something like that. Why would you want, for instance, an interval that had a super low percent confidence associated with it?